Alrighty, I think might go ahead and get started. Hope everyone's doing well today. Welcome to the stream. So, what are we gonna do today? So the goal for today is we're gonna look more at the wave equation. We talked about it a bit last time. Derived the wave equation from just an infinite series of harmonic oscillators, and so today I wanna dive a bit more into the meat of the wave equation. So the first thing we're gonna kind of start out by looking at wave interference and how what happens when we start adding different waves together, and more how we can use it as a tool later on for actually solving the wave equation with specific boundary conditions. Then we're going to go a bit more into these sort of special boundary conditions that we can choose for the wave equation that might be interesting in certain physical scenarios, which will naturally lead us to the idea of a Fourier series. I'm sure people have heard of Fourier series, Fourier transforms, all that, and so hopefully today we'll get a little bit more into what all that stuff is and how to use it. And then kind of towards the very end, we'll get a brief glimpse of how all of this stuff can get generalized to the idea of a Fourier transform, which is going to be a much more general tool that we can have at our disposal that we'll be talking about a lot more in the future. So, of course, as always, if you have any questions, feel free to drop them in the chat. I try to read it as I go. I see that Rodrigo has a Quantum Mechanics 2 exam, so good luck on that. Hope it goes well. But so yeah, feel free to drop questions in the chat. I'll try to answer them as I go. But okay, so let's just start. What is the wave equation? Well, wave equation, we can write it in terms of a partial differential equation, where we take two time derivatives, and this is equal to what we found is the speed of sound times two space derivatives. So this is the one-dimensional wave equation. So 1D wave equation. We're going to stick it in 1D today. We're not going to venture out to 2D, 3D, any of that for the time being. So just to sort of get the idea behind what's happening. And where phi, this guy here, phi is just some fluctuation. It might be a actual like amplitude of the height of a wave. It might be a pressure density, whatever we might want it to be. We can just think of phi is just whatever function is following our wave equation. And of course, phi is going to be a function of both space and time, hence why we're able to take derivatives with respect to each. So, last time, we showed that we can solve this equation by doing a method known as the separation of variables, where we assume that phi is a function of x and t. We can split it up into just a product of some function which only depends on time and some function which only depends on space. Now, when we did that, we ended up finding that we essentially get two equations for a harmonic oscillator. And so, writing that out, can see that our function of time is just given in terms of some cosine of omega t plus, I'll call alpha 2 sine omega t. where omega is just, it's a constant. It's a number that we put in. And if you want me to go through this derivation again, I certainly can. But like I said, we did this last time. But so in a similar way, we have our function of x, kx, plus beta 2 sine kx. And of course, alpha 1, alpha 2, beta 1, and beta 2 are all constants that we fix with boundary conditions. But this isn't the end of the story. We also needed to require a certain condition on omega and k in order for the wave equation to be satisfied. And that's what we call is equal to the speed of sound squared times this k squared. Okay, so that's sort of the recap. Yeah, if you have any questions, of course, let me know, but can move on. So this is sort of generally true, but what we also saw is that in the special case of the one-dimensional wave equation, we could also write our solution, phi of x and t, as a sum of some function x plus ct, which is a left-moving piece which moves to the left, plus g of x minus ct, which is a piece which moves to the right. So this is true in general. We just fix these, and these are the functions which we now fix by boundary conditions. Okay, so now something that I sort of briefly mentioned last time, but I didn't really expand upon too much, was this idea of wave interference. And so wave interference happens. So wave interference happens when, so if I have some wave, which I don't know, maybe it looks, oh wow, that's awful. Maybe I have a wave which looks like this between 2 points, and I want to add it to another wave, which, I don't know, maybe looks like this. It's more spread out. Then the end result is that essentially I'm just adding the two waves. So let's see. So you can see that I can essentially just superimpose this wave here on top of this wave. And I'll get something which looks like this. Might not be perfect, but where you can see this wave here, I'll make this wave blue. I'll make this wave red. So you can see the shorter wavelength wave here in red. Whereas the longer wavelength, you can see, is still living here in blue. Right? And this is the whole idea behind wave interference. What you'll typically see it as is split into two different pieces, which is constructive interference. Which is essentially when I have two different pieces, and in this case, I'll just represent them as little bumps, plus another little bump. And since they're both positive, they're going to add together. And the end result is going to be just essentially a bigger bump. And then there's destructive interference. I'll come down here to write. Destructive interference. In which case, I can look at these two bumps, except maybe I invert one of them. And the end result of this is that the two will cancel out. And the idea being that these two add on to each other, hence constructive, and these two destroy each other, hence destructive. Okay, so as an example of this, why don't we take, so remember, we can write our wave equation as f of x plus ct plus g of x minus ct. And why don't I make these two, this left moving piece and this right moving piece, just essentially make them equal to the same thing. And we'll just make it a Gaussian wave for simplicity's sake. So call this e to the minus ax squared. So that, of course, this guy here is just equal to 1/2 e to the minus x plus ct a squared plus 1/2 e to the minus a x minus ct squared. Okay, so what happens when we do this? Well, we get exactly what I was saying. You get two pieces of the wave coming together. They add together to get a bigger bump, and then they keep moving along their way. So this is constructive interference when the two waves meet, and then as soon as they've stopped overlapping, you see that the constructive interference is no longer there. Okay, so we can do the same thing for destructive interference, and so maybe in this case, instead of having them be the same, we'll have them be opposites. So we'll say that g of x is minus f of x. And we'll make this the same thing here. So in this particular case, what we'll see is something very similar. We get these two bumps coming towards each other. But you see, as soon as they start to overlap, they start to cancel each other out. But again, they eventually move along their way, and this destructive interference is no longer there. It only exists when the two pieces of the wave are actually overlapping. Okay, so that's sort of the general idea behind interference. It's probably a concept a lot of people are familiar with, but I wanted to address it a little bit more more in detail. But more importantly, what I really want to do is use this idea of interference as a tool. So what I'm going to say is, instead of having an infinite string, right? So instead of having a string which extends all the way to minus infinity, plus infinity, I'm going to cut it in half. Okay, I'm going to just erase this part, and I'm going to pin down the piece at x equals 0. Pin it down so it cannot move. So, in other words, I'm specifying a boundary condition on my wave. Specifically, I'm specifying that at x equals 0, for any time, I don't care what time I'm at, it should always vanish at x equals 0. Okay? So now, I still have to specify some other boundary condition, so I'll say that on this string, I'm going to start with some left-moving wave, which is described by f of x plus ct. So for the time being, we're going to pretend we don't have a or we're going to enforce that we don't have a right moving piece of our wave, and we only have this left moving piece. Okay, so now, I mean, this is fine, but we run into a bit of an issue because we can't just say that phi is equal to x plus ct, because that doesn't work. Because this doesn't necessarily always vanish at x equals 0. You can see that as this wave moves to the left, eventually, right, I'll draw some time pieces in the future. It's going to be here, and then it's going to be here, and then we're going to run into an issue because this is going to describe something like this, and it's no longer going to be vanishing at x equals 0. So how do we get around this? Well, we can use a tool which comes from this idea of interference. So what we'll do is, instead of cutting the string in half, so let me get rid of these and rid of this. What I'm going to do instead is I'm going to extend this string back to x equals infinity, but do so in a way that whatever I have on the x less than 0 piece is always going to exactly cancel what's going on at x greater than 0. So that this point here always vanishes by just wave interference, right? Anything that happens on the left is going to exactly destructively interfere with whatever's happening on the right at x equals 0. Okay, so how do we do this? This seems like a fairly nebulous thing, but how do we do this? One very easy way is to just say that whatever we choose, I'll erase this because this isn't true. Whatever we choose for phi, and remember, now phi is going to be describing what's on the whole string, from negative infinity to positive infinity. We're just going to make this anti-symmetric, so that if I were to mirror everything, it flips. So, in other words, I just mirror it. Ooh, that was awful. Mirror it over here, but in the opposite amplitude, if that makes sense. So invert the amplitude so that now it's negative over here. And also I'm going to want this to be moving to the right. So another way of saying this is just, I'm going to take phi as a function of x and t, and I'm going to say that that should be equal to its negative when I flip the spatial component. So when x goes to minus x, I just get a negative sign. You can see this. So if here this is sitting at x equals 1, then this is sitting at x equals minus 1. And they're just exact negatives of each other. Okay? And you can see that this tells me that at x equals 0, phi, I can say 0 goes to minus 0, and I still get 0. And this is only ever going to be satisfied if it's 0. 0 is the only number which is its own negative. So you see, this is automatically satisfied. This automatically takes care of everything. So I essentially automatically get my result for the wave equation. And this gives me something which looks like phi x is equal to my piece over here, which I know that I started with, and I'm just subtracting off the x reversed piece, so the piece where x goes to minus x. And that, of course, just gives me ct minus x. Okay? And so now I can essentially forget about whatever's happening on the left-hand side here, I can pretend that that doesn't exist because in the physical system I've already said it doesn't. I'm only concerned with what's happening on the right-hand side. But I can still treat my wave equation as if that piece does exist. So this idea is known as the method of images. Where I've essentially created an image wave. Again, I'll just draw this in red. So this is my image wave, what I might call, which isn't really a piece of the physical system, but I use this as a tool to satisfy my boundary conditions. And I get a function for my wave. So what does this look like when I consider something like this? Well, it's going to, again, I'm just sticking with Gaussians here because they're easy to picture. So remember, we start out with some left-moving piece, but on the left-hand side of this, for x less than 0, we have that image wave, and what you'll see is this piece which moves to the left eventually hits the origin, and the piece which is moving to the right, this imaginary piece, now takes over. But all we've really done is described a reflecting wave, right? This is a wave going, hitting a fixed point, and then reflecting off of it. And instead of having to do a bunch of, messing around with satisfying boundary conditions, we were able to get this by just essentially enforcing some sort of destructive interference. And actually, if you'll notice, this is exactly the same as what I showed here. If you were to essentially cut this picture in half and only look at the right-hand side, this is exactly the same thing as what's happening in the reflecting wave case. You just see what's happening on the image, the imaginary part of the wave that we put in by hand on the left-hand side. So that's sort of how we can use this idea of interference as a tool to actually solve the wave equation and other systems as well, for certain boundary conditions. Okay, so yeah, from this point forward, I'm going to be mostly talking about Fourier series and all that good stuff, so I think this is probably a good place to take a quick pause, see if people have questions, all that. And I guess I should note, if people want to ask questions while I'm saying this, go ahead. Can also note that we could include the right moving pieces as well. To this, we just get something which looks like g x minus ct, and then minus the x reversed pieces. Minus x minus g of minus x minus ct. Something like that. Okay, so now I'll take a quick pause, see if people have questions, and then we can move on to something which I personally think is a little bit more interesting, more fun. Okay, well, I'm not seeing any questions showing up. So why don't we go ahead and move on? So we just considered the case where we cut our infinite string in half and consider fixing down one of the endpoints of that string. So what if, instead, we not only cut the string in one place, but we cut the string in two places, and we pin down both ends of it. So we'll say that we have a string like this. Say it has length L, length big L, and both ends of it are pinned down so that they cannot move. Okay, so the fact that these can't move means that the amplitude, like before, has to always vanish at each of these points. So we'll call this point x equals 0, call this point x equals L. And so again, we just get a certain set of boundary conditions that we impose on our solutions to the wave equation. So this just means that we have a boundary condition which looks like this, where just at each of the endpoints, amplitude has to vanish. So now we could do this with our left moving and right moving pieces and all that stuff. We could actually even use a similar idea of method of images, but it actually a lot of times is a lot more convenient to use our separation of variables solution. So just to quickly write that out again, it's something like this, where t alpha 1 cosine omega t, alpha 2 sine omega t, then x is beta 1 cosine kx plus beta 2 sine kx. And then, of course, our dispersion relation. Excellent. So it actually ends up being more convenient to use this, mainly because this boundary condition is only seeing the x piece. So it's actually a boundary condition on x and not t. So we can write this as x of 0 equals x of L equals 0. Okay? The first one is easy enough. So x of 0, so sine is going to vanish. This first term is going to vanish. This guy is going to be 1. So this is just going to be beta 1, and that has to be 0. So we see that this cosine term drops out. We're only left with the sine term. So we have x at L is equal to beta 2 sine of k times L, and that also has to be 0. Okay, so there's sort of a couple of choices here, which we can do. We can, of course, choose beta 2 equals 0, which is the incredibly boring solution, and that nothing ever happens on our string. It's always the amplitude everywhere is always 0. So that's not really what we want. We want something interesting, something that will give us interesting dynamics. So instead, let's ensure that sine, the sine term, always vanishes when x is equal to L. So we want sine of KL equals 0. So when does sine vanish? Well, sine vanishes. So sine vanishes, I guess I'll write this as sine of theta vanishes for theta equals minus 2 pi, minus pi, 0, pi, 2 pi, etc. Right? All of these values, sine is going to vanish. So whenever, so when theta, which in this case is KL, is equal to some integer, which I'll call n, times pi, this is going to vanish. So we actually now get a expression for k, so this wave number, and I'll just call this k sub n, and this is n pi over L. if k is equal to this for n integer, then we're guaranteed to have this sign of KL vanish, and our boundary conditions will be satisfied. Okay? So, just writing this out quickly, we have that x of x is equal to some beta 2 times sine of n pi x over L. And this ensures that both at x equals 0 and x equals L, that our wave, or the amplitude of our wave, will vanish, just like we need. And again, I'll just, I don't need to write the n as an integer, I'll just underline it here. Okay, so now we can't forget that we have a dispersion relation. So not only did we find a relation for k, we also found a relation for omega. So we know that omega squared, I'll say omega sub n, is equal to c squared times k sub n squared, which of course is c squared n squared pi squared over L squared. So this is going to actually give us two solutions. I'll call this n plus minus, right? Because when I take the square root of both sides, I get a plus piece and I get a minus piece, so on. So for each k, I'll actually write this as plus or minus k. For each value of k, I essentially get two values of omega. Now, remember what we were talking about last time, and that when, at the end of the day, what we want to do is we want to take all of these possible solutions that we get for these wave numbers and frequencies and all of this, and we want to add them all up. So in principle, we should be taking both of the pieces for any given k, we should be adding up both of the omegas. But this is actually redundant, and this is redundant because of the fact that cosine of minus x is equal to cosine x, and sine of minus x is equal to minus sine of x. So these are known as the symmetry properties of the function. Symmetry properties. In particular, you'll often hear people say that cosine is even, and this just comes from the fact that when I take x to minus x, I get the same thing, whereas sine of x is odd, and that just comes from the fact that I get this minus sign. Another way of saying it is cosine is symmetric, sine is antisymmetric, however you want to say this. But whenever I refer to the symmetry properties of cosine and sine, this is what I'm talking about. But anyway, so when I try to add these two values of omega, I'm going to get, so just keeping the constants sort of general for the time being, omega t plus b prime cosine minus omega t, right? Because I have to have the positive and negative piece. Plus c prime sine omega t plus d prime sine minus omega t. You can see that I can use these symmetry properties and essentially pull out common factors of cosine and sine and write this as just some a cosine omega t plus b sine omega t. Where I just defined a is a prime plus b prime, and b is c prime minus d prime. So this just essentially lumps constants together. And you see that the two solutions actually end up being somewhat redundant. So, going back to our solution, remember that, I'll I'll write this for one of our normal modes. That's what these are. These are just normal modes, just like for harmonic oscillators. This is going to be t sub n of t times x sub n of x, which I'm just going to write as, call this a prime sub n cosine omega n t plus b prime sub n sine omega n t, right? So this is the t part, and then the x part, which is just sine of k sub n x. And that's one of my normal modes. But to get a general solution to the wave equation, I have to sum over all of these normal modes. So my general solution is going to be given by phi of x t. Sum, right now, we're going to say the sum goes from minus infinity to infinity. A sub n prime cosine omega n t plus b prime sine omega n t times sine k n x. Okay, we're almost there. It turns out that there's still even more redundancy. And again, this just comes from the fact that, secretly hiding, we have omega n is some cn pi over L, and kn is equal to n pi over L. So that when I take n to minus n, I again see this sort of, redundancy from the symmetry properties of the sines and cosines, right? So when I do this, cosine doesn't change, and sine gets a negative sign, so I can essentially pull out common factors of cosine and sine and just lump the constants together, so that now I can rewrite this as only a sum over positive n starting at 1, because if I try to start at 0, I just get 0 because of this guy. And I'll just write this as a n cosine omega nt plus b sub n sine omega nt times sine k sub n x, where I just defined a sub n is equal to a prime sub n minus a sub minus n prime, and b sub n prime plus b sub minus n prime. A's get a plus because can't forget, or get a relative minus sign because you can't forget the negative sign coming from this guy, and the b's get 2 minus signs, one from the k, one from the omega, and so they get a plus sign relative between them. So this here is essentially every solution to the wave equation with 2 fixed endpoints. It's every single one. I just have to find a sub n and b sub n for whatever boundary conditions, and I've solved it. I've solved my problem. Now, granted, that's oftentimes easier said than done, but okay. Get into how I'm going to do that next, but I want to again take a quick pause, see if there are any questions, and drink some water, all that good stuff. Hopefully this is all making sense. I know it's a lot of math, but sometimes you just gotta get through the math to see the interesting physics light at the end of the tunnel. And honestly, the math tends to be pretty interesting along the way, so. Okay, so I guess I'll go ahead and move on. So, what have we done with this? So, I said this the last time, in a sense, but I want to reiterate this here. What we've done is we've essentially just taken our general solution, found some set of what I'll call basis functions, and expanded our general solution as a linear combination. So this sum of individual basis functions in almost exactly the same way that we might in three-dimensional space write a vector as this sort of linear combination of basis vectors. Idea being that these cosines and sines are acting very much like these basis vectors here. But this sort of begs the question. I want to find these coefficients, right? These coefficients A and B, which correspond to, in this sort of analogy, they correspond to this Vx, Vy, and Vz. Now, in this case, I can, say, pick out V sub x by just projecting my vector onto one of the basis functions, because all of my other basis functions, or I guess this should be x hat. I'll call this x hat. Because I know that, x hat dot x hat is equal to 1, x hat dot y hat is equal to x hat dot z hat is equal to 0. In other words, these are all orthonormal. So the question is, can I do a similar thing? Can we do a similar thing for phi, for our general solution? Is there some way we might be able to project onto the individual basis functions and get a general solution? Or and pick out these coefficients in the same way that we pick out the x coefficient by just projecting v onto the x hat direction. So the answer is, of course, yes. I probably wouldn't be asking the question unless the answer was yes. But so to do it, what I'm going to do is I'm going to just take some fixed time slice and do things in maybe a bit more, maybe less general, maybe more general, depending on what you think of it. But essentially, what I've said is I can take n equals 1 to infinity, any function which has two fixed endpoints, n pi x over L, and expand it this way. So if I have x in 0 to L in this range, and I know that f of x vanishes at 0 and L, I can always write it in this way. I can always expand it out in terms of these signs. And you can see that's all we did here, right? Really, this whole thing here is just a coefficient at some fixed time. But so the real question is, are these signs orthonormal in the same way that these x's, or x hat, y hat, and z hats are? Yes, they are. And to see it, I want to consider an integral, specifically this integral. 2 over L integral from 0 to L. So over my whole range, I'm integrating over my entire range. And I want to take two of these basis functions over L sine of m pi x over L. And I want to ask what this is equal to. So to do this, we can use a trick, and that trick is looking at this trig identity. Cosine theta plus or minus phi is equal to cosine theta cosine phi minus plus sine theta sine phi. Which then means that sine theta sine phi is equal to 1/2 times cosine theta minus phi minus cosine theta plus phi. So now I'm just going to use that theta is equal to n pi x over L, phi is equal to m pi x over L, and I can rewrite this integral as 1 over L, because of the 1/2, integral from 0 to L over x, and this is cosine of n minus m pi x over L minus cosine n plus m pi x over L. And now all I'm doing is taking the integral of cosines, which is fairly straightforward. We can just look this up in a book, whatever it may be. And when we carry this out, we find that this is equal to sine m minus n times pi divided by m minus n pi minus sine of m plus n pi over m plus n pi. Okay, so now remember that m and n are positive integers. Well, they're positive, and they are integers. Which means that m plus or minus n is also an integer. Not necessarily positive, because if you subtract the two and n is greater than m, then of course you can get negative, but it's always going to be an integer. Which means that this term here is always going to vanish, no matter what, right? We already said that sine of an integer times pi is always going to give you 0. Since m and n are positive, then the argument in the denominator is never going to go to 0, and we're fine. Now this first term is almost always 0. Almost. Except for the one scenario where m is equal to n. So in the case where m is equal to n, so if m is not equal to n, the integral just gives 0. Always gives 0. So already we're off to a great start, because we see that at least all of the basis functions are all orthogonal, right? If I choose two different ones, then I get 0. This integral, which is essentially, we're treating it as the analog to this dot product that I showed up here for vectors. This gives us 0 when m is not equal to n. Now in the case where m is equal to n, it's a little bit tricky, because at first we might think that this is giving us 0 divided by 0, which looks very, very problematic. However, we can use a trick and look at this limit. Limit as x goes to 0 of sine of x over x. Now, there's a few ways of doing this. You can use L'Hopital's rule, you can do a whole bunch of stuff, but what I'm going to do is I'm going to Taylor expand sine. So we've looked at Taylor expansions in the past, and so sine gives us something like x minus 1 over 3 factorial x cubed plus dot dot dot, all divided by x, which is going to give us limit as x goes to 0 of 1 minus 1 over 3 factorial x squared plus yada yada, which is just going to give us 1, right? All of these terms of higher order in x, those all vanish when I take this limit, and I'm just left with this first term. So this gives me 1. But you'll notice this ratio here is exactly this ratio here. And the limit as x goes to 0 is just the same as the limit as m goes to n. So what we see is that this integral, so 2 over L, integral from 0 to L, dx sine n pi x over L, sine of m pi x over L is equal to, well, it's 0 if m does not equal n, and 1 if m equals n. I can write in a little more compact way as this Kronecker delta. So this is defined as the Kronecker delta. So this, of course, looks very familiar. So if I call my basis, so familiar from the case of vectors, if I call my basis vectors, maybe E1, E2, E3, I know that E hat n dot E hat m is also going to be equal to the Kronecker delta, assuming these are orthonormal basis vectors. So we see that this is all very much analogous. We have some solution in our, we can think of it, space of all solutions of this wave equation with fixed endpoints. And it's given by a linear combination of these basis functions, these sines of n pi x over L. So going back to our full solution to the wave equation, so writing it out again, n equals 1 to infinity, a sub n cosine omega nt plus b sub n sine omega nt times sine of k sub n x. Then I can just use this integral and multiply both sides by sine of k sub m x. So I'll get something like 2 over L from 0 to L dx by xt sine of, write this out, m pi x over L. This is equal to n equals 1 to infinity. Actually, I'll just pull out all the stuff that doesn't depend on x. B sub n sine omega nt. Ooh, I'm gonna run out of room here. 2 over L, 0 to L, dx. Yeah, I'm gonna run out of room. So it's this times integral from 0 to L dx sine of n pi x over L times sine of m pi x over L. We know, of course, that this gives us our Kronecker delta, which collapses this sum to a single value. And I'm able to fix my fix these constants as long as I know by at some time, or at 2 times, really, or its derivatives. Dx by x comma t sine n pi x over L. And so this is how I find my particular solution to the wave equation using this Fourier series. I just use my orthogonality relationships by means of this integral. I integrate both sides, get the Kronecker delta, collapse the sum on this right-hand side to a single term, which then I know is just given by this integral. Okay. So let's look at a particular example. And I mean, we'll do a particularly straightforward example as well, where we'll say our initial condition at t equals 0 is some sinusoidal function. So 2 sine pi x over L plus 5 sine of 5 pi x over L. And then we'll say that we give it some initial velocity, which is going to also be sinusoidal. 6 sine of 3 pi x over L. Okay. So now we just have to do this integral, right? So if I integrate 0 to L, 2 over L, dx phi of x comma 0, sine of n pi x over L. Well, this is only going to give me something non-zero for 2 values of n, right? So for n equals 1, this is going to give me something, well, this is just going to give me 2, right? Well, and actually, I'll write out what I have on the right-hand side here. So at t equals 0, this sine term drops and I'm only left with the cosine. So this is a sub n. So, like I said, I only get 2 non-zero cases for n, which is n equals 1, in which case I find that a sub n equals 2, and then n equals 5, in which case this as n a sub 1, a sub 5 is equal to 5. And then all other a sub n's vanish. Okay? So the second equation is going to be, well, it's not going to be exactly this, because first I have to take the time derivative, but it's essentially the same thing, where I get that, so sorry to go back and forth like this. So when I take a time derivative, so d phi dt is equal to this sum of omega n a sub n sine, this should have a negative, minus omega n a sub n sine omega n t plus omega n b sub n cosine omega n t times, and obviously the time derivative isn't going to touch sine, or the x term. So that at t equals 0, d phi dt at t equals 0, this term's going to drop, and I'm only left with this, which is going to be omega n b sub n sine, this sum of k sub n x. So then to find omega n times b sub n, I just do this trick of integrating with the orthonormal basis functions. So this is easy enough, remembering that omega n is cn pi over L. I get that cn pi over L times b sub n is 2 over L times this integral from 0 to L dx, and our time derivative at t equals 0 is given by this. So this is 6 sine of 3 pi x over L times sine of n pi x over L. And you see that the only non-zero term is the n equals 3 term. So here I get something like 3c pi over L, b sub 3 is just equal to 6. And so b3 is equal to 2L over c pi. Okay? And that's it. That's our solution. That's our wave at any time. So I'll write it out a bit more explicitly. Cosine c pi t over L sine of pi x over L plus 5 cosine of 5c pi t over L sine of 5 pi x over L, and then plus this 2L over c pi sine of 3ct over L sine of 3 pi x over L. Be a pi in here. Okay, and that's given these particular set of initial conditions. This is my wave. This is it. This is the solution. So you see, mathematically in general, this can be very difficult. Doing these integrals in the cases that these aren't just super simple sine functions can get very tricky. But conceptually, there is nothing too bad about this. This is just, we take an integral which is just projecting onto a single one of our basis functions, and that gives us our coefficient, which we then just plug into the Fourier series. So, I mean, what is this describing? So again, this is just describing a superposition of waves. So it's a certain set of interfering waves, which we can see here. So these are the 3 different pieces, which we found. And as I evolve this, so the red pieces are the individual basis functions, which make up the final wave equation solution, right? So you can see how they interfere both destructively and constructively together to give the full solution in black. I think it's a very, very nice looking evolution of the system. But yeah, so you can see this is not super simple motion that we got for a fairly non-intensive or mathematically not super intense method. Yeah. So again, I think I'll take a quick pause here. If people have any questions, feel free to ask. And then move on to a similar but slightly different scenario. Okay, well, yeah, I'm not really seeing anything. So let's just keep this train moving. So now, instead of having a case where we have two fixed endpoints like this, right? We looked at a string which had two fixed endpoints where everything had to always vanish. Let's instead consider it's related. It's not exactly the same, but it's closely related. The case where our string might be a loop. So it's a closed loop. We don't want to cut the loop. And so we have to impose, again, some sort of boundary condition on our solution to the wave equation to make sure that we aren't cutting this loop. And to do that, what we'll say is that, I mean, if I start here, and then I go all the way around the loop, I should end exactly where I started. In other words, I have that phi of x, x comma t, at any fixed time t, this should be equal to x plus L comma t, right? Where L is you can think of it as the circumference of this loop. It's L. That's a weird way of drawing it, but oh, thank you, Jacopo. That's very kind of you to say. Okay. So again, this is just a condition on the spatial component, which means that we can translate this to just the x. So this is that x of x is equal to x plus L. We know that x is this sum of sines and cosines, right? And we also know that if I have a sinusoidal function, if I have, say, sine of theta, this has to be equal to sine of theta plus 2n pi. Right, because that's sort of the idea of a sine, is it's oscillatory. And if I go one full rotation or two full rotations, whatever, if I go through an integer number of rotations, the sine and cosine functions, cosine, theta, just ensure that I end up exactly where I started, n pi. So, what can I do? So I can say that if I have, again, where theta is equal to k, kx over L, I believe. Yes. So here I'll say theta is kx over L. So then when I shift, this theta is just kx. Apologies, messed that up. So then when I take x to x plus L, right, so I'm going from this piece to this piece, then I know that theta should go from kx to kx plus kl. But this should just be equal to kx plus 2n pi. Right, because this is just what I have in the arguments of my sines and cosines. So this is what I should get when I make this shift. So you can see that I can pick out this piece, and I can pick out this piece. And I see, again, I get a condition on k. And I get that k this time is 2n pi over L. Where again, n is an integer. But this is the only condition, which means that I can't just get rid of sine, or the cosine terms this time. So I'm stuck with the cosine terms, along with the sine terms. And so, again, with these same arguments of the redundancies of the omegas and the k's and all of this, I can write my solution as the sum, whoops, have to have this constant term, n equals 1 to infinity. This is going to be quite the expression. Hopefully I can fit it all. Cosine of, I'll write this as c k sub nt plus b sub n sine c k sub nt times cosine k sub n x plus c cosine c k sub nt plus b sub n sine c k sub nt times sine k sub n x. Okay, this looks like a lot. I should comment on this this guy here. This just comes from the n equals 0 piece. Remember beforehand I only had this sine term and the n equals 0 piece just always vanished. Here it doesn't always vanish, but it only gives me a constant. It doesn't give me any t's or x's or anything like that. It's just some number. And so that's this a0 over 2. The divided by 2 is just a convention. So don't get too worried about the why it's divided by 2 or anything. It's just a convention. Okay, so this is a again a different type of Fourier series, this time for periodic functions. So functions where the only condition I've imposed on them is that they end where they started. It doesn't have to be vanishing, it just means that given some range, so I'll write this sort of like I did before. So for x in some range, it can even be some L or a to a plus L, where a is some number. It doesn't have to be 0, it doesn't have to be whatever. It can be any range. And f of x equals f of x plus L. I can expand a function that satisfies these in a similar way to how I did before. Sub n cosine n pi x over L. Whoops, 2 this time. B sub n sine of 2n pi x over L. So this is another Fourier series. It's a Fourier series for a different type of function, and this is an important thing to keep in mind when you're dealing with these. So in the earlier case, we only had the sines, and that was when the endpoints were fixed, right? The endpoints were fixed and vanishing. Here, I don't necessarily fix the endpoints. I don't force them to vanish. I just require that it's periodic, so I end where I start. In this case, I get both the cosines and the sines. Okay? Hopefully that makes sense. Hopefully you buy that. Okay, so now we have to make sure that we're still dealing with orthonormal functions, right? So we proved it for just the sines, but now the argument in our sine has changed, and we also have this cosine riding along. So we have to do a little bit more work this time. Now, we'll consider very similar integrals, except this time I'm going to use the range minus L over 2 to L over 2. Like I said, this particular, for the periodic functions, this is all satisfied for a general range, but the symmetric range is the most convenient to deal with. So in this case, let's go ahead and check the case of the sines. We already did the sines, so let's go ahead and check this again. So we can use a similar trick. I'm not going to go through this in super close detail because, like I said, already essentially did this. N pi x over L sine of 2m pi x over L. And when you go through the work of solving this integral, you get something like this. Sine of m pi minus 2m cosine m pi sine n pi all divided by m squared minus n squared times pi. Okay, so again, we see that for m not equal to n, this vanishes. This just gives me 0, right? Because I have integer times pi here, I have an integer times pi here, it's always going to give me 0. For m not equal to n. But for m equals to n, I get a similar story, where it looks like I get 0 over 0. So I should really take this limit again. So I'll just write this out as 2n over pi. So when I take this limit, I get something like cosine n pi sine m pi minus cosine m pi sine n pi over m squared minus n squared. Now this looks complicated, but at the end of the day, we just do the same thing as we did before. We just Taylor expand n around m, all this stuff, yada yada yada, and we get something 2n over pi, limit as m goes to n, sine m pi minus n pi over m squared minus n squared. And just like before, we find, not super surprisingly, that this just gives me 1. So again, we find that for the sines, minus L over 2, dx sine of n pi, 2n pi x over L sine 2m pi x over L is again just the Kronecker delta. Now it's a bit more involved to show it over a more general range, but that's why we choose this symmetric range, just sort of for convenience. But you can show that this is also true for any range, for this general range a to a plus L. You can show that this is true. Now, again, we can do a similar thing. I'm not going to go through it in super close detail because it's almost identical for the cosines. And again, not super surprisingly, we find something like 2m pi x over L is also equal to the Kronecker delta. Okay, so our sines are all orthonormal to each other. Our cosines are all orthonormal to each other. But we still need to check that sines and cosines are mutually orthogonal. Okay? So, of course, we could do this in the exact same way, where, we expand out the integral in using trig identities, do the integral, take limits, whatever. But there's actually a nicer way of doing this, and it's a good, I guess, shortcut to use whenever you can. So if I have cosine of 2n pi x over L, sine of 2m pi x over L, I can split this integral up into two different pieces. I'll write this as 2 over L. One piece which goes from 0 to L, cosine 2n pi x over L, sine of 2m pi x over L. And then this plus a second piece, which goes from minus L over 2 to 0. Cosine 2n pi x over L, sine 2m pi x over L. Now, in the second integral, so I'm just going to take this second piece here. I am going to take x to minus x, which means that this negative sign in this bound disappears, right? So minus L over 2 then goes to L over 2, and then 0 goes, it stays as 0. So when I have the dx, I now get a minus dx, so a total minus sign. Integral from L over 2 to 0 dx cosine of 2n pi x minus L sine of minus 2m pi x over L. Now, I can flip the bounds, so instead of going from L over 2 to 0, I go from 0 to L over 2. When I do that, I get an overall minus sign. So that gives me something like, we'll just erase this minus sign, erase these bounds. This gives me 0 to L over 2, but positive. Negative cosine of a negative is equal to cosine of the positive, so that negative sign is completely irrelevant. And the negative sign in the argument of the sign flips the sign of everything, so this gives me a negative. So you'll notice that this second piece of the integral is exactly negative this first piece of the integral. So this sum here is always going to give me 0. So this is super important. This is actually a super important thing to keep in mind. So I'll write it up here. This is why the idea of the symmetry of the functions you're dealing with is very important. I have a symmetric range about 0. Right, I'm going from minus L over 2 to L over 2. It's symmetric on either side of 0. I have a function which is also symmetric multiplied by a function which is anti-symmetric. Which means that, so this is where the idea of even and odd comes from, but I have an, so I have a symmetric function times an anti-symmetric function, which overall gives me an anti-symmetric function. Right, so if I have phi, or f of minus x is equal to f of x, and g of minus x is equal to minus g of x, then f of minus x times g of minus x is equal to minus f of x, g of x. Right, so the total product is anti-symmetric. So, when I integrate an anti-symmetric function over a symmetric range, I always get 0. Always, 100% of the time. It doesn't matter. Okay? And just sort of to intuitively see why that is, that's just because we know that a function like this is summing up the area between a curve and the x-axis. So if I have some anti-symmetric function, I don't know, maybe it looks something like this between these two points, you can see that this part is always going to exactly cancel this part, and this part's always going to exactly cancel this part. So no matter what, due to the anti-symmetry of the function, it has to always give me 0. End of story. Very important thing to keep in mind to simplify integrals. But anyway, back to what we were dealing with. So we have our orthonormality relations for sines and cosines. So I'll write them out again, just so that we have them. Sine of, wanting to do the other one, pi x over L, sine to m pi x over L is equal to delta nm 2 over L minus L over 2 to L over 2, cosine to n pi x over L sine to m pi x over L equal to the Kronecker delta, and then sines and cosines, n pi x over L sine of 2m pi x over L equal to 0. So these are my three orthonormality relations for my functions. Okay, so again, I want to just take a quick break. We're going to do some more manipulating these Fourier series, and then start talking a tiny bit about Fourier transformations. But in the meantime, of course, if you have any questions, feel free to let me know. I'm going to take a moment, have some water, answer anything that shows up. Okay, well, not seeing anything. So, okay, so we have this Fourier series, right? I mean, it's a bit of a mess. Let's see, where did I write it down? Yeah, this guy. It looks complicated, and that's mostly because cosines and sines tend to be a little bit cumbersome to use. You know, writing everything out tends to be a bit of a pain, proving relations with them. You have to use all these trig identities and all this stuff. And it turns out there's actually a much simpler form for this type of a Fourier series. And to see it, we can use this nifty property that we've proved on a previous stream, where e to a complex power is equal, or I guess to an imaginary power, I sine theta. I can, of course, invert this to give me that cosine is e to the I theta plus e to the minus I theta over 2, and sine theta is e to the I theta minus e to the minus I theta over 2I. So I can plug this into my Fourier series, and I get something which looks like f of x. So again, this is the Fourier series for periodic boundary conditions. Sum from n equals 1 to infinity of a sub n e to the I k sub n x plus b sub n e to the minus I k sub n x, where I just defined new constants, a sub n minus I b sub n over 2, and then b sub n equals a sub n plus I b sub n over 2. Now, we have to be a little bit careful here, because we might be tempted to just right away say, okay, well, I mean, obviously, a sub n is just equal to b sub n, the complex conjugate of b sub n. But we do have to be a little bit careful, because there can be cases where this function itself is complex. In which case, since going back up here, so if f of x is complex, the cosines and sines are real. These always spit out real functions, which means that your a's and b's here would have to be complex. So if that's the case, then this here is not true. Right. I mean, you can see that if a and b are, or if capital A and capital B are complex numbers, then little a is not the complex conjugate of little b. However, if f of x is real, then this is true. So, right, if all my capital A's and capital B's are real numbers, then this is true. So then I can write this just as x equals a naught over 2 plus sum from n equals 1 to infinity a sub n e to the I k sub n x plus a sub n complex conjugate e to the minus I k sub n x. So this is only true if my function is real. Now, something I can do is looking back at this guy here. If in this second term, I just take k to minus k, right? So I know that k sub n is 2n pi over L. Then in the second term, if I take k to minus k, I get something like b sub minus n e to the I k sub n x, which is exactly the same basis function as which shows up here. So now, if I go back to having my sum be over all values of n, instead of just positive values, I get, and just calling, just renaming these constants here, I can write this as just the sum from minus infinity to infinity now of a sub n, I don't even need the parenthesis, e to the I k sub n x. That's it. That's all I need. Okay? And now it's pretty straightforward to see that if f of x is real, then a sub n is equal to the complex conjugate of a sub minus n. Right, because for the negative values of n, I know that a is just equal to this b sub minus n. And I know that if f is real, then a sub n is just b sub n complex conjugate. So that's a very nice constraint that we have in the case that f of x is real. And again, I will just write it because it's important to always remember. And this is, of course, for just periodic functions. Periodic functions. If you try to do this with a non-periodic function, the result will be very angry at you. You'll get some very, very highly oscillatory stuff happening at the ends of your range because you're essentially the series is trying to essentially force everything to be periodic. Okay, but so we have different basis functions now. So we should check that our basis functions still are orthonormal. And now you can already see this is much nicer because we only have a single orthonormality relation to check. And we can check it with this integral here. X to I n pi x over L x of minus 2I m pi x over L. And again, without going super deep into the details, this is a pretty straightforward integral to do. We get something like m pi minus n pi over m minus n pi, which we already saw. We already saw that function, and we know that this is the Kronecker delta. So we're still dealing with orthonormal functions, and all is well and good. And we can go one step further and show that our coefficients are going to be given by 1 over L minus L over 2 to L over 2 dx f of x e to the minus I k sub n x. Right, the minus is coming from this minus sign here. Okay, and remember, this minus sign is the n's and the m's are allowed to run over both positive and negative values now, right? So that is something which is important to keep in mind, but that's yeah. Okay. So anyway, back to the wave equation. Let's take all this stuff, all this formalism, and plug it back into the wave equation. When we do that, we can see that in this new fancy way of writing things, our solution is going to be given in terms of just complex exponentials as e to the I kn x minus ct plus b sub n e to the I k sub n x plus ct. And so here you can see that already we can write this as some f of x minus ct plus g x plus ct. I think I had it backwards with f and g before, but regardless. So you see we're all the way back where we started. But this is one of the ways that we can really clearly see this relation. You could get to this with the sines and cosines as well, using trig identities and all that, but it's a very clear, very easy way of seeing this, just by expanding out the sines and cosines and what we had before in terms of complex exponentials. Okay, so only a little bit more to talk about today. And the first thing I want to bring up is there's actually in all of this is sort of hidden. It's an extra orthogonality relation. We've seen a few of these so far, but there's actually an extra one that's been hiding there all along. And to see it, we'll look at these coefficients. So we'll start by saying that this guy, the x, f of x, e to the minus I k sub n x. So these are our coefficients in terms of the function itself. But we also know that we can write, here I'll call it f of y, is equal to the sum, and this is going to seem all like, well, yeah, you already told us this, but there's a method to the madness. why I'm doing this. So again, I'm just writing out this Fourier series again with a new variable y. So what I'm going to do is, in this equation here, I'm going to multiply both sides by e to the iky and just sum over n. Right, so on the right-hand side, I get this, a sub n e to the I k sub n y, which, as we said, is just equal to f sub y. This is equal to 1 over L times the sum from n equals minus infinity to infinity, integral L over 2 to L over 2, x, f of x, e to the I k sub n y minus x. Right, the minus x coming from this guy and the plus y coming from this guy, wherever you want to see it's coming from. Okay, so what is this telling us? This is saying that this sum here, 1 over L, n equals minus infinity to infinity, e to the I k sub n y minus x. It's telling us that this is actually a special thing, right? So you see that when I integrate, it doesn't matter if I do the sum first or the integral first. So let's say I do the sum first. So when I integrate after doing the sum, I get exactly the function that's in the integrand, except evaluated at this point here. So I'm just going to call this something else, some new function. Call it delta. And I use the term function loosely. Technically, I believe this is known as a distribution. But us physicists aren't particularly great with all the mathematical language, so I'll end up calling this a function, and mathematicians can yell at me for it. In particular, this is known as a Dirac delta function. Or oftentimes just delta function for short. So what this delta function does is it says, okay, so I take this integral from L over 2 to L over 2, f of x delta x minus y. This is just equal to f of y. So it picks out the value of the function at a particular value of y. But this is essentially, as long as y is in this range, minus L over 2 to L over 2. Otherwise, the integral would never see this value, and you're screwed. But so, yeah, you can see that if I essentially replace the sum, or replace this integral by a sum, and my x with some discrete value, and my y with some other discrete value, this delta function is essentially a generalization of the Kronecker delta. Kronecker delta. So, for example, if I have some over minus n to n, I don't know, of a sub m delta mn, this just gives me a sub n. Right? It's the same thing, essentially, except now the Dirac delta function deals with continuous variables. Okay? So, what does this look like? What does this function look like? Well, it has to be 0 for every value that isn't, for every value x not equal to y. So, delta x minus y is equal to 0 for x not equal to y. And we can see this by essentially breaking up our integral. So minus L over 2 to L over 2 dx f of x delta x minus y. And I'm going to break it up into tiny little pieces. So L over 2 minus L over 2 plus epsilon dx times all this stuff plus minus L over 2 plus epsilon minus L over 2 plus 2 epsilon dx, and so on and so forth. So sort of schematically, what am I doing? I have L over 2 to L plus L over 2, and I'm just cutting it up into little tiny pieces. So now, when I have my function, I don't know, whatever my function may be between these 2 points, to have this be equal to only f of y, so say y is here, none of these pieces can ever contribute to the integral, right? Only the piece, so all of these have to cancel, except for this piece here, in the small neighborhood of y. So everywhere else where x is not equal to y has to be killed. It has to be killed off by this delta function, so it has to be equal to 0. But here's the problem. So I have something on the left-hand side. So if I just look at f of x, delta x minus y, this is only defined at a point. So this is, or I guess, only non-zero at x equals y. But it gives me some finite result. Now I know that I can interpret this integral as a sum of all of the little areas under the curve. But if I have an area under a function which is only non-zero at a single point, right? So this function really looks something, like this. To have some non-zero area under this has to be formally infinite. So this is infinity. It's a bit weird to think about, but it has to be. There's no other choice. You don't get another option. To have a finite area underneath a single point, that point has to live at infinity. Now, I'll say this is this is all sort of technical stuff, right? In most cases, these technicalities don't come up, but this is important to know that the delta function has this weird property of being formally infinite at a single point. But the really important property of it is the fact that when I take this integral, it picks out just this single point. It evaluates my function just at this single point. That's the very important property of the delta function. Another thing to notice is that the delta function actually has units, right? So in this case, whatever dimensions x has, so say x has dimensions of length, you can see that for the dimensions to match on this left-hand side, so f is going to have the same dimensions over here as over here, and that means that the dimensions of the delta function has to be 1 over the dimensions of x. So the delta function, weirdly enough, also has units, and it's going to be, the units are going to change depending on what you're integrating over, what variable you're integrating over. It's just a weird property of delta functions that, again, is important to keep in mind when you're dealing with them. It helps with sort of bookkeeping to make sure you're doing everything correctly. Okay, so I'm going to take one last quick pause before moving on, and the last thing I want to talk about is Fourier transforms. So sort of generalizing what we just did to the case of, maybe we don't have just a loop. We do have an infinite string. Can we still do the same thing? And what we'll see is that, yes, we can, but we have to use a Fourier transform instead of just a Fourier series. And this Fourier transform is going to end up being an incredibly powerful tool for us to be able to use. Okay, so if anyone has any questions right now, feel free to ask. More than happy to answer anything. I'm gonna quick pause. Okay, so no questions popping up. So let's go ahead and crank this out. So okay, so we're gonna take our Fourier series, right? Where did I define this Fourier series? We're gonna take this Fourier series for a periodic function. And what I'm gonna do is I'm just gonna take the constants first. I'm just gonna rescale them. They're just constants, so I can do that. And I'm gonna rescale them by 2 pi over L instead of equals a sub n. And this 2 pi over L, I can write as delta k a sub n, right? So where delta k is equal to k sub n plus 1 minus k sub n plus 1 minus k sub n, which of course 2 pi over L. Now there's a very important reason why I'm doing this, and that's because so I can write out this function minus infinity to infinity delta k a sub n e to the I k sub n x. So now, to get back to our infinite string, so our string which doesn't necessarily have to be periodic, don't have to fix any endpoints, what I can do is I can just take L to infinity, which of course is the same thing as taking delta k 0. So when I do this, this sum here is going to become an integral, right? So in this case, if I'm going to lasso this stuff, move it over, I'm going to say this is the limit as delta k goes to 0. This just becomes an integral from minus infinity to infinity over k. And these a sub n's are now going to become functions of k, which I'll call f tilde, e to the I k x. Now, this whole thing is infinite, which means that I no longer have to specify any periodic boundary condition. Right? It's infinite, so I'd have to go all the way around to infinity to be able to get back to where I started. So I don't have to require periodicity anymore. So actually, this is going to end up being valid. This relation here will be valid for any function as long as I can do this integral. If I can't do this integral, it's not valid. But so most cases that we're going to deal with, this will always work for most of the cases that we're going to be dealing with, I should say. So this is very important. This is the Fourier transformation, or Fourier transform. Okay, but we have to be a little bit careful here, because when we found all of our orthonormality relations before, they all relied on the fact that things were integers, that these m's and n's were always integers, and so these signs went to 0, or I took these limits, whatever it may be. So can I still say that all of these exponentials are orthogonal or orthonormal? So it turns out that we can, and to see it, we can look back at our delta functions. So remember that our delta functions, delta x minus y, is equal to 1 over L times sum from n equals minus infinity to infinity, e to the minus I k sub n, x minus y. So here I can write this just rewriting L as 1 over 2 pi, n equals minus infinity to infinity, delta k, e to the minus I k sub n, x minus y. Right, so I just used this relation here to rewrite L, or 1 over L in terms of delta k. And now I take the limit. So now I take the limit as L goes to infinity and delta k goes to 0. Now notice nothing over here depends on L or delta k. Only the stuff on the right-hand side depends on that. But you see here, again, I'm going to end up with an integral when I take this limit. And so I'm going to end up with a relation for my delta function, which looks like 1 over 2 pi, integral from minus infinity to infinity, dk e to the minus ik x minus y. So this is given now in terms of continuous variables. And this actually is an orthonormality relation, right? You can see that this is so this is an orthonormality relation, between e to the ikx, or e to the minus ikx, and e to the iky. Right, it's the same thing. So we can use this to find 1 over 2 pi minus infinity. So this is just another way of seeing that this is in fact an orthonormality relation. Is I take these, what were my coefficients, but are now coefficient functions, I'll call them, which depend on k. E to the I x k minus k prime. Notice that this relation here, it doesn't care what value I'm integrating over. This could be x, this could be k, whatever. It's just some variable that I integrate over. As long as it's multiplied by this stuff in the exponent, I get a delta function. So here I get a delta function between k's when I integrate over x. So this is integral from minus infinity to infinity, dk f tilde of k delta k prime minus k, which of course is f tilde of k prime. So again, you see that this is an orthonormality relation. I've used this integral to single out one of my coefficient functions, just like before when I used the integral over sines or complex exponentials when I had discrete arguments. um, it picked out just a single one of the coefficients. So again, we're doing the same thing here. It's just that now we're picking out a function, or a function defined at a single value of k. So in other words, I can write this f tilde of k, right? So I can use this, use the right-hand side of this, multiply both sides by e to the minus I k prime x, and then integrate over x. I also need this factor of 1 over 2 pi. 1 over 2 pi minus infinity to infinity dx f of x e now to the minus I k x, right? So this, I'll write out the other one again, equal to integral minus infinity to infinity k f tilde of k e to the I k x. Together, we have a Fourier transform and an inverse Fourier transform. Along with our definition of a delta function, which I'll just write again to be safe, dk e to the minus I k minus y. And it doesn't matter if this is plus or minus. It's the delta function is actually a symmetric function. But okay, so this is kind of where I want to end things. I don't want to get too deep into Fourier transforms because there's a lot to talk about, so I'll probably do that on the next stream. But I just want to sort of make a note that this is sort of, you know, in physics at least, this is one of the first instances of what we call a duality, where these x and k variables are very different things. They describe incredibly different things. So what we'll see is that x describes obviously a position. A lot of the time can use time, whatever. And k describes some sort of, if x describes position, then k's typically describes some sort of momentum-y type thing. If x is a time, then k describes a frequency. So you can see these variables are very different things, but the functions defined on the space of those variables are related. So in other words, I can describe the same physics. So I can, if I have some physics described by f of x, I can describe that same physics by f tilde of k. So these are two very, very different things describing the exact same physics. And that's the idea of what we call a duality. So if you've seen stuff about ADS-CFT duality, all these dualities showing up in supersymmetry and string theory, all of this stuff, it might seem crazy, but we have one right here. We have a duality right here. We have two very different functions defined on two very different spaces, which describe the same physics. And that's all we mean by a duality. So with that, I think that I am gonna call this stream. If anyone wants to ask any closing questions, feel free. Again, I'll be more than happy to answer anything. But that's all I really have. Okay, well, I am not seeing anything come up. But I think I might wrap up here. Yeah, I'll say thanks again for all the support, everyone. Really appreciate you showing up and checking these out. If you're watching later, YouTube, I still appreciate you. Hope you enjoyed this, and be excited to see you for the next one.